This talk has only one idea, and if you get it, I'll be very happy. And it has to do with thing that has bugged me from my youth. We are all kind of raised in Newtonian straitjacket. I mean, we are very indoctrinated how we think about physical description of the world. And the basic idea is that if you have some symmetry, some intuition about the system, and you perturb things by a little bit, you end up writing ordinary or partial differential equations. And those are various variants of, that we have inherited from Newton. And the other thing that is very important to us as humans, and that there is time, and time is different from space. Time is different from space. So you go out, you look at the clouds, they obey a version of Navier-Stokes equation, more sophisticated, but basically that's the idea. And you have this totally insane thought that there is a supercomputer in the sky that goes chaka, 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 and clouds are doing whatever they're doing because they're being integrated forward in time. Now, we're indoctrinated in so many things in our life that we take without questioning. But this is a total insanity. This is not how the nature works. So I would like you to take from this talk that maybe we should listen and see how the nature does it and try to do it ourselves. So nature doesn't integrate Navier-Stokes equations. Does it obey Navier-Stokes equation? Yes, but it doesn't integrate them. What it does is it knows that I'm a molecule. There are all these other molecules around me. I just have to make sure that I'm okay with my neighbors. I can't stick out too much. I can't do this. That's called local conservation law, or that's called the partial differential equation that you write down to describe it. So locally, that's true. If you're a dancer, you cannot turn your hand 360 degrees around because it's not possible. So there are laws that you have to follow, but the nature doesn't use supercomputers. The way I think about it, it's not just as a physicist, but in a very general sense, there are lots of problems that we have to solve. So here we are combining fancy version of fluid mechanics with fancy version of biology, maybe neuronal system. And it's the same thing is true there. Neurons don't know about your equations. The brains don't know about your equations, whatever you're imposing on them. But they do have to obey the constraints that, they have to obey. There is a law and you have to follow it. How does the nature do it? Here's an equation. It's a little bit too complicated to illustrate. I'll illustrate it a little bit in this talk because I'll show one video from solving Navier-Stokes equations. But the rule of this talk is we're given the law and we have to obey it. There'll be no statistical assumptions. There'll be no Gaussians, no nothing. We just have to follow the deterministic laws. This is not a quantum mechanics talk. And the reason why we have to do this is that experiments have gotten totally amazing. We have so much insight about how the fluids work. We actually have to provide the theory that explains what we see, and not just provide some statistical average and some slope and survival rate, whatever. And the standards are much higher today. So experiments are amazing. Theory and numerics have gotten to be amazing. So, I'm just putting some random pretty pictures that my colleagues produce. But, the things that my colleagues can produce today couldn't be done 10 or 20 years ago. They're totally out of, range of possible, and they couldn't be measured that they measured today. So here is one possible thing you might want to construct here a turbulence that doesn't, belong to Newton, but might belong to Leibniz, not to Newton. And that is that when we look at this is a simulation, but the experiments are similar. We look at the very complicated big thing. Would it be possible to take blocks of it and from it glue turbulence together? Is there some way? Now, that seems like too naive because these are nonlinear problems. So we know that we cannot add two solutions and get solution. But how could we do this and what would it look like, this kind of theory? So to illustrate it, I'll do one Navier-Stokes, but it's easier just to illustrate it in one-dimensional Navier-Stokes, which has various versions. One is called Kuramoto-Shivashinsky, just because you can visualize it and you can comprehend it. So this is a typical solution of one-dimensional Navier-Stokes or flame front on some finite but large domain. And it has a property that it's either spatiotemporally chaotic or turbulent. As you go in time is going up, space is horizontal. And the heat map is telling you how fast is the flame front moving on a ring of Bunsen burner. And it is a remarkable property that here you can visually see space-time. And you have all the information about Kuramoto-Shivashinsky by looking at this solution. So it's a very nice thing to look at. It's much harder to do this for full Navier-Stokes. Our task as people who explain how laws of nature work and what their consequences are to explain this kind of picture. We have to, doesn't suffice to just average it and get 0.723 out of this thing. This is too late for that. So one thing that's very important for us is that whenever we put these things on computers, in principle, they're infinite dimensional because they're fields, so there are functions defined every place in continuous space-time. So if you think of dynamical systems, they have infinitely many dimensions. In practice, we stick them on computers, so they have finite number, but very large. The things that you do in fluid dynamics require at least 100,000 computational elements, or what's called dimension state space, and typically a million or something like that. Now, one thing that's important is that cloud has insanely many dimensions in that sense. But when you look at the cloud, you say, well, this is not Flavio Fenton. This is a cloud. And how do I know this? I know this by the shape of the cloud, right? So there are some features, and it really helps to be a little bit nearsighted and not see too much detail to be able to identify them. So we know that even though this is a huge dimensional problem, actually it's very low dimensional because we as humans can classify it and sort it out. So the mathematical statement of this is called the dimension, physical dimension, or it's called dimension of inertial manifold, some word that people use in fluid dynamics. And today we have very precise meaning what this dimension is. And for example, for Kuramoto-Shivashinsky, we have a beautiful result that says that no matter how complicated my Kuramoto-Shivashinsky system could look like, actually the number of dimensions that contains the attractor of the system is finite. It's not like there's some kind of fractal cloud and it's centered in a finite dimension. It's finite. It's a number. And that number can be computed very precisely as the shoulder in this plot. And if you disregard the fact that your dimension is already taken care of, and for example, you recompute, this is Lyapunov spectrum, doesn't matter what it is, but if you recompute this is twice the precision, so you over-resolve the state space, only thing that will happen, you'll stick lots of points here in the right-hand part, which is not the physical part. These are the dimensions in a problem in which you are falling into the attractor. And the attractor, no new information will obtain by over-resolving it. So that's, a very strong result. It says that in dissipative flows, they actually live, they're embedded. There's a body bag, there is a flow, you're in million dimensions or 100,000 dimensions. And inside of that, there's a manifold, which is much, much smaller than your space that you're computing in. And that's where all the action is. And that's what we share between, let's say, plasma fluid dynamics theory of brain or neural networks. They also have, low-dimensional manifolds on which things happen that are only important things that, brain does, cortex, muscular cortex, or whatever it does, motor cortex does. So that's one thing that we have. Mathematically, even though these problems are very high dimensional, there is a low dimension of information contained in them. The other thing is we used to kind of discretize these problems, stick them on computers. Typically what we do is we say, a pipe is infinite, but, I can make it periodic and I can compute my solution on this for arbitrary times. So that's how all the simulations are done, that you watch various beautiful plots that you see. They're done typically by compactifying the space. You can compactify time and you can integrate in space. That also works. But what doesn't work is that when you're looking at systems which are intrinsically unstable, you actually cannot integrate forward in time much beyond their point of time. And the same is true of space. So it turns out that these simulation codes, if you really want to predict the flow, they only work for finite time and finite space. And if somebody tells you that I can, run my dynamical system in infinite time because I have a shadowing lemma, I will ask you to go to Blackboard and show how shadowing lemma applies to Kuromoto-Shivashinsky or whatever. So we have to rethink how we compute it, but we know that nature solves these problems and it doesn't care about the Puno horizon. So how does it do it? So one hint is that if you look at this picture of Kuromoto-Shivashinsky I've shown you, and you look a little bit closely, little myopia, you put a little window and run it around, you discover that you see the same thing over and over and over. So this thing actually is built from, in this example, there is a defect that you see all over the place. So can we use these kind of small things to build the big things? I will go very fast, but I will show you one Taylor flow, one example of how these things work. So what's done here, this is a simulation of a flow shared by two plates. It's turbulent. On the left-hand side is a snippet of turbulent flow. On the right-hand side is one of my compact solutions, which look like one of those defects, if you wish. And what the flow illustrates is that there are instants in time where when this turns black, I cannot distinguish the ergodic turbulent flow from my little approximation to it, which is invariant, and it's part of my vocabulary, and then I lose it. The way that nature solves these problems is that locally it has to satisfy the thing, and globally it has to satisfy the boundary conditions. And when you think about clouds and other forms this way, there's no time evolution and no space evolution. You're just trying to make sure that a solution is globally true every place. This is something engineers do routinely, and it turns out that sounds impossible because you need lots of coordinates to do it, but it's actually much more efficient than going forward in space and time doing PDs. And you can do this without crazy accuracies. And engineers can do it. So here's an example how you find a global solution of Navier-Stokes. You start with something, which is not solution, and you find solution very quickly. This idea that we can build stuff from the blocks is you can study various solutions in Kuromoto-Shivashinsky, and you can extract from them the smallest little blocks that compose the global solutions. Here is an example of starting with 3 of them. And then you can glue them together. That's what's shown there on the left. This is not a solution. This is just a bunch of things that you glue together to see where I can get a solution. You can find a nearby solution that looks exactly like that. In other words, you can use the little blocks as symbolic alphabet in space-time. and construct larger and larger solutions of your systems and do your computations on them. And when you do this, you've forgotten all about dynamics. There's no time in this. You're just finding a repertoire of solutions. Can you do it? There is a bunch of people who have shown that you can. There is, public codes that exist. And if you are called Jane and you want to choreograph a dance, the first thing you have to do is you have to learn a repertoire of postures and movements that dancers can do. And then you can use that alphabet, as I've shown you for Kuramoto Shibashinsky, to start building choreography. And it's totally essential that all the solutions that you have are unstable. That enables you to explore the space of all possible dances. And that's it. I propose that when you go home, you say, maybe I don't need to solve an ordinary partial differential equation. I mean, I know they taught me this in school, but Leibniz, thought otherwise. Maybe I should find everything that's allowed, and then from these blocks, build up the world that we see. And I claim that when you're looking at unstable system, that's the only way you can proceed. Integrations in space and time don't work. I'm done.